Hello everybody, this is Avantik here. Today we will be discussing about ensemble methods. The agenda for discussion would be understanding what is ensemble methods, random forest, AdaBoost, gradient boosting tree and voting classifier. Let's first start with introduction to ensemble methods. Introduction to ensemble methods. The objective of ensemble method is combine predictions from several base estimators like decision tree. Okay, don't get confused with the term over here. Base estimators is any of the algorithm that you have discussed so far. Okay, it can be nearest neighbor, it can be linear regression, decision tree, all this algorithms. Okay, and create a combined effect of all of them. Okay, so to understand, we will get into types of ensemble method, and then we'll get into details around it. But what is essentially happening, you are combining different base estimators and creating a cumulative impact. Let's understand different types of it to get deeper into what is ensemble methods. The first one is averaging method. To understand this diagram was very useful, and thanks to the person who created it, it's very easily available in internet. Okay, so this is a single model base estimator. You can assume this to be decision tree over here. Okay, this is a simple model. Now what you do in averaging method or bagging method, same thing. Okay, you will create replaceable samples from the data. Okay, you can see here you are creating n samples out of the data, and you will use this n sample to train n models independently. So at the end of it, you have n, assuming decision tree, n decision tree trained independently of different samples. To do the prediction, we will use all these independently trained trees to do the prediction, and your final prediction will be a function of all these data. For example, whatever, in case your class, you're trying to do by class classification, so whatever is in majority, that will be the verdict of new data, right? For example, if you have 9 such decision trees trained, if more than 5 or more than 5 class decision trees predict the data belongs to class A, that will be your final verdict. This is your averaging method or bagging method. Here the training is happening parallelly. The next method is boosting method, which is little different from your bagging in the sense that it is sequential. You know, so you have you in this case also you configure number of decision trees or any other base estimators, but the training happens sequentially. Okay, so assume you have a first decision tree, you have the data, you're training the model, and there is some misclassification. The data which was misclassified will be given higher weightage. We'll get to those details, but the data which is misclassified will be given higher weightage, and it will be used for training again. Okay, so you can see this cannot be parallelized. This is sequential here. The output of this will change the data, and the data will be again fed to the new model. So in this case also, you'll have n trained models. Okay, and your final prediction will be function of all this prediction of this individual model. We'll be getting the details around it, but this is the fundamental difference between bagging and boosting. Okay, so let's get into our first bagging method, that is random forest. Random forest is a example of averaging ensemble method. Before we understand it, first let's just recap on the limitation of decision tree. Fundamentally, decision tree overfits and shows high variance, right? That was the limitation of decision trees. Okay, so now random forest tries to generalize the behavior of decision trees. Okay, let's see how it is done. Okay, this is the whatever data we have. Random forest splits the data into n samples, depending what is the number of trees you want to consider, n samples. You'll use all these samples independently to train n different trees. Okay, and during this process, the number of features that will be selected will also be varying between different trees. Okay, so to see the algorithm, that's what data consists of r rows and m features. Sample of training data is taken. Okay, so for each tree, sample of training data is taken. Randomly you will be selecting some features, right? Features are the columns. Randomly you will be selecting some subset of features from the data. Okay, so and you will be using it for training different trees. Okay, and you generally would allow the tree to go in based on your target. The tree can be classification tree or regression tree, and let's assume for our understanding that the tree is a classification tree. So based on the data, different trees will be trained. Okay, now your final verdict for a new data would be, you pass the new data, it will go through all the trees. Based on the trained structure, each tree will give its verdict. Okay, and your final verdict will be majority voting. That is how random forest for classification works. In case of regression, it whatever is the value predicted by each tree, it can either calculate mean or median. That will be the uh, target value in case of random forest regression. Let's see some code around it. Okay, and we are using MNIST data now. We're loading digits. We have seen this multiple time, and we are using random forest classifier, which is residing inside Ensemble, right? And then you have model selection. You are splitting the data into train and test, this part, right? Pretty much common code. And first we are using decision tree, right? We are training the model, and once the model is trained, we are doing validation. We get an accuracy of around 84%. Now without any hyperparameter. Now without any hyperparameter, I train my random forest as well, which will internally use by default uh, by default 10 decision trees, right? And once I train and now I predict, it is 94%. So without doing a lot, we can see here that random forest behaves more generalized or more better than your decision tree over here, right? There are some hyperparameters which are of high importance in case of random forest. Let's go through them. One is n estimators, right? N estimators we didn't configure in our previous code, but n estimators tells you how many trees will be created, or basically how many subset of data will be generated from the main data, right? That is n estimators. The more you configure is better, but there is of course an optimum point beyond which the model stops converging. Okay, and of course there is a compute cost associated. The next parameter is max features. Okay, max feature is number of features that will be used in training in training a particular tree. Okay, in case of classification, you can configure the square root of number of features. In case of regression, your max features can be equal to number of features. This is like common practice. Okay, n jobs should be configured as -1 so that you can leverage multiple core computing in this case, because averaging method can be parallelized. Another important other advantages of random forest are minimal data cleaning and dealing with missing values required. So you're all good with that. Works very well with high dimensional data sets. Okay, and minimizes variance. Even for random forest, we can find importance of each features. Okay, so if you do the train model dot feature importances, in our MNIST data we have 64 features, right? So it is giving you features of all those columns. So based on this, we can select the important features and use that only for training the model. Okay, so that's dealing around random forest. And next we will be getting into AdaBoost. AdaBoost. Boosting in general is about building a model from the training data, then creating the second model that attempts to correct the errors in the first model, right? This is what we discussed earlier as well. So you train your first model, okay? Whatever misclassification is, you assign some higher weightage. We'll see that. And you'll try to make sure those misclassified data is correctly classified in the next model, right? And you continue doing so. AdaBoost is one of the first boosting algorithm that came into the picture, right? And it can be used for both classification and regression. Let's understand the algorithm now. Okay, so it also, like your averaging method, relies on some weak learners or base estimators like decision trees. Okay, but how it is different from averaging method here? The training will be sequential, right? Initially, each training data is assigned equal weightage. Okay, once and you have an empty model, untrained model. Now once you train it, whatever data was misclassified, you will increase weightage of those data, and whatever data was correctly classified, you will decrease weightage of those data, right? And you will train again a new model, right? A new model will again be trained, and you will continue doing this till all the data is correctly classified or maximum number of iteration is received, right, is achieved based on your configuration. Your final prediction would be prediction coming from all the individual trained trees, right? It will be a function of that. Okay, so let's play around with AdaBoost classifier. So we are configuring base estimators as decision tree, and we are configuring equivalent height to that. Number of estimators 600. That means uh, it will do the iteration 600 times, right? And once you train the model, we are validating, it is showing you 98% accuracy, right? And we can use random forest inside AdaBoost classifier, right? Beautiful, isn't it? So here also we get around 96%. So of course we don't gain much out of it, but we can see that it can consume random forest, though this is not something that is highly recommended, just for fun. Okay, after this we'll be getting into gradient boosting trees. Gradient boosting tree, a boosting technique which is based on decision tree and is suited for both classification and regression. Just to go back to the linear regression, let's recap what is this residuals. This is the fundamental assumption. The sum of residuals is zero. What that means is, if you have a predictor, right, if you have a predictor, then the mistakes is basically called residuals. Okay, so uh, for ideally the sum of residuals should be as close to zero, right? For if the model's sum of residuals is not close to zero, okay, we can leverage that in trees as well. Generally it's a concept of linear models, but we can leverage that in trees. Okay, sum of residuals is the distance between, or the value between the actual value and the predictor and the prediction, right? That's the thing. And the fundamental assumption of linear regression is sum of residuals is zero. Okay, so now if the residuals is not zero, then there is probably a pattern in the residuals, and this is what gradient boosting tree tries to leverage. Okay, it tries to, it tries to converge, it tries to minimize the residuals, and in this process it converges new values of parameters. Okay, so that's what it will use. You based on the loss function configured, okay, in the model, it will use that and try to minimize the residual. Okay, in this process the algorithm is boosted. So that's what the concept here is. So let's see how it is done, how it is configured. So again, we are using housing data here, and we are using gradient boosting regressor. Okay, in gradient boosting regressor you have few important things. One is loss. Okay, loss, ls, least square errors, right? So it tries to minimize this value, and in this process, this whatever changes it has to do in the model, it tries to do that. Okay, so you can see here the same gbt I'm using, and and number of iterations, number of n estimators in this case is configured 100, as you can see here, right? So we want to know how does the loss function, loss value improve with number of estimators. So we have this gbt dot stage predict, which will predict at every stage what was the loss. Okay, gbt dot stage predict test x enumerate, and this is giving you the loss value. Gbt dot loss is the actual value, this is the predicted value. You can see beyond 20 it is going down. I mean, it's pretty much stabilizing, right? So number of trees, number of estimators 30 around is good for this. And we can see that it tries to converge, it tries to minimize the loss, least square, right? That's what it tries to do. This was gradient boosting tree, a very good algorithm. And you might be hearing about XGBoost and all those are all modifications of gradient boosting trees. Voting classifier. The core concept of voting classifier is to combine conceptually different machine learning classifier and use a majority vote or weighted vote to predict the class or labels. Okay, so for example, you have a lot of estimators like RandomForest, SVC, nearest neighbors, right? AdaBoost, logistic regression. Your final prediction, I mean, one way to do that is whatever is majority using different models. So as you can see, it can have ensemble methods as a base estimator here, right? So there are two types. One is soft voting classifier, one is hard voting classifier. In hard voting classifier, all of them have equal weightage, and that's the first example we have done, right? We have all this configured, right? And we are configuring voting is equal to hard. That means all of them have equal weightage. So once you train it, right, fit, it will train all of them and it will do the prediction. And once you do VC score, it is giving the score using what is the final verdict. Okay, if you want to see what is the individual accuracy for all this model, you can do vc.estimators train model, and this is the estimator 0 will be giving you name of the model. So RF will be name, and here you see this is the accuracy using random forest independently, using SVC independently, nearest neighbor classifier independently, uh, AdaBoost, logistic regression. But when you combine them, you get an accuracy of this. So this is supposed to be more generalized, as you know, since you're taking multiple models into consideration, you have low variance. The each individual's limitation is overcome, right? And the other technique is using voting as soft, and you can assign weightage to different classifier. Like RF will have two, SVC will have one, nearest neighbor classifier will have three, and these two values is 2 2. Okay, so you then fit the voting classifier with this data and you get a different accuracy. Now your nearest neighbor will get higher preference, right? Its verdict has higher importance.